Great, let's explore this. SpaceX's Starship spacecraft currently cannot fly to the moon on its own, and of course, it's also not capable of continuing the journey to Mars. To make such a flight, each Starship will need to rendezvous and refuel from other spacecraft in orbit before it can continue the journey beyond Earth. This is an orbital refueling method that has never been tested in the history of space exploration. It's not only a breakthrough, but also a major surprise to the global scientific and technological community. All of this will be revealed in today's episode of AlphaTech. One of the most important design goals of Starship is full and rapid reusability, consuming only fuel during launches. But more than that, the big goal of Starship is to support SpaceX's ambition to make humanity a multiplanetary species and build a self-sustaining city on Mars. To make this happen as soon as possible, SpaceX first needs to complete NASA's mission. To conduct flights to the moon and beyond, SpaceX not only needs to build the most rapidly and efficiently reusable rockets and spacecraft ever, but also must master the technique of orbital refueling. To ensure that refueling goes smoothly in space, Starship must meet three critical requirements: the ability to dock in space, maintain fuel at cryogenic temperatures, and transfer fuel between spacecraft. Each of these challenges is an essential factor in ensuring the success of long-term missions beyond Earth's orbit. First is the issue of docking. While it may seem simpler than the other factors, it is still a crucial step. SpaceX has gained significant experience from docking spacecraft with the International Space Station, ISS. During refueling missions, Starship will need to dock two large spacecraft in orbit, one to store fuel and one to receive it or carry out missions. With the advantage of controlling both spacecraft, SpaceX can ensure precise alignment and docking. Success in docking cargo and crew vehicles with the ISS has laid a solid foundation for these operations. Next is maintaining cryogenic temperatures for the fuel. This is a more complex challenge, as it requires storing liquid oxygen and liquid methane at extremely low temperatures. Maintaining a temperature of 2 Kelvin for liquid oxygen and 112 Kelvin for methane in space is a major challenge, as there is no gravity to help separate liquids from gases in the tanks. If the fuel is not properly cooled, it may boil and reduce the fuel supply for the mission. SpaceX is researching passive cooling methods, such as special surface coatings and orienting the spacecraft to reduce heat absorption from the sun. NASA is also contributing critical insights into cryogenic fluid management, particularly through the use of cryocoolers that have been proven in applications such as MRI machines and space missions. As for fuel transfer in microgravity conditions, SpaceX uses small thrusters to push the liquid fuel toward the bottom of the tank, while another method involves cooling the receiving tank to create a pressure difference that forces the fuel to transfer. These techniques have been successfully tested by NASA in ground experiments and partially in space, such as in the RRM-3 mission. The RRM-3 mission in 2018 demonstrated the ability to store cryogens long-term when it arrived at the ISS, although a hardware failure prevented the demonstration of methane transfer in orbit. Nevertheless, this mission validated key concepts for in-space refueling and showed that with continued development, these technologies could be feasible for future missions. The technical challenges of orbital refueling are significant but surmountable. SpaceX can leverage proven techniques and enhance sophistication in space operations. The number of refueling flights required for Starship remains unclear, with estimates ranging from at least 5 flights to over 20, depending on payload capacity, Starship's mass on the moon, and the specific requirements of each mission. Although the exact number of flights has yet to be determined, what matters most is SpaceX's ability to perform them efficiently and reliably. If only 5 flights are needed, the process could be straightforward and achievable with current technology, assuming that Starship's design meets or exceeds the necessary requirements. When estimating up to 20 refueling flights, the challenge becomes much more complex. Conducting a large number of flights in a short time requires SpaceX to maintain a high level of operational activity and reliability, with an increased risk of delays or failures. However, SpaceX's strategy of rapid reusability helps mitigate these risks. Starship and the Super Heavy booster are being developed with extremely fast turnaround times, promising a level of reusability far beyond current space vehicles. If SpaceX can launch and land the same Starship multiple times within days or even hours, managing 20 flights will become more feasible. This could reduce the time and cost for each mission. SpaceX's reusable launch system is designed to enable frequent flights without significantly increasing costs. The relatively low fuel cost doesn't change much with the number of flights, while the efficiency of launch operations, a field in which SpaceX has already demonstrated its capability with the Falcon 9, is key to effectively managing multiple Starship flights. Conducting multiple rapid consecutive flights could make large-scale refueling technically and financially feasible. Competitors like Blue Origin have pointed out that, according to SpaceX's data, an HLS version of Starship would require an additional 15 flights to refuel for the trip to the Moon, with 14 flights supplying fuel and 1 flight for the HLS Starship to transfer 1,200 tons of fuel. However, Elon Musk has refuted these claims, stating that all the refueling work can be done in 4 to 8 flights. In April 2024, Musk said that only 5 or 6 refueling missions would be needed for each trip to Mars. He believes SpaceX can achieve this with an expanded or improved Starship tank version, and promised that within the next year, the company will demonstrate the ability to transfer fuel between spacecraft. Fuel transfer between 2 spacecraft may seem complex, but NASA accepted the risk when it chose Starship as the lunar lander for Artemis 3 and 4. Kathy Lueders from NASA acknowledged that carrying out this mission could lead to delays due to its high complexity. However, other options, such as the Dynetics and Blue Origin landers, faced significant challenges, making Starship stand out with capabilities far exceeding the HLS requirements. Starship can transport 100 tons of cargo to the Moon, helping to reduce costs for the Artemis base station. SpaceX's bid of $2.9 billion is only half that of its competitors, thanks to Starship's ability to launch satellites. Over the past year, SpaceX and NASA have made significant progress in developing the Starship HLS. 4 test flights have improved the rocket's reliability, and over 200 docking system tests have been completed. Leaked render images show that test results are being integrated into a stronger design for the lander.